We're going to look at conservation of energy, or are we going to find that energy is not conserved? And we're going to find out with a pendulum, an activity with a bowling ball or a softball, and predict what happens when you pull a ball on a string to one side and let it go. Explain why. Making a pendulum fixed securely to the ceiling, installed by a qualified adult on strong, thick enough nylon twine, attached by an adult with ladder training. And please, students cannot do this activity with the bowling ball. Even professors have had their noses broken. So it's a pendulum. So how can we test conservation of energy with the motion, the swinging motion of the bowling ball as a pendulum? And hint, there's a chair. So a responsible adult will sit in the chair. And that person must not move their head, and they must not push the bowling ball, just let it go freely. And so what happens when the responsible adult lets go of the bowling ball? Pause the video to make your prediction and include in that how far will the bowling ball go, and will the bowling ball swing back and hit the person? So, keeping very still, let the ball swing back and forth several times, and as you observe it, write down how close it gets to the person's nose each time. We can also do this with a softball. So again, pause the video to predict on letting go, the softball traveling away from the person, does it stop at A or B or any other place before it returns to the person? Explain your answer. So, what happens to the softball with complete conservation of energy? And this is no loss of energy to its surroundings. The softball would reach B, sort of a mirror image from where it starts, before returning. But in reality, the ball maximum distance is slightly less far than the position at B. So, what causes the kinetic energy loss? Again, pause to answer the questions. What happens to the lost kinetic energy? Where does it go? So, the same thing will happen when the bowling ball is let go. Remember, you're not pushing it. The ball doesn't go quite as far as a mirror image, the furthest distance following the swing. So kinetic energy is lost, and with the bowling ball, where is that energy lost? So, will the bowling ball swing back and hit the person when it swings back? Why? Why not? Remember, the ball is let go, it isn't pushed. In position number 1 on the left, person holding the softball right by their nose, the ball has the maximum potential energy. And as it goes through the arc, at the lowest point, it has 0 potential energy at number 2. Travels to B, travels back through A, and as it travels back through A, it has the maximum kinetic energy. It's going the fastest. And so let's see this in a real lab situation.
Attached to the lighting up there. Earlier this morning I experimented with 2 other bits which were fun. One was I had a little, it was like this on it, which is a bit dull. So then I went for something, a lot heavier, made of lead. I thought that would be fun, that'll be good. That's a real nose breaker. But unfortunately I think it was going to break the light. because the whole thing was creaking and moving. So that had to come down. So in the end, we've got these slightly more, but nonetheless exciting softball. All right, so the question is, I am going to sit here, relaxing, drinking coffee, and I'm going to release this from the tip of my nose, and like that. And then I'm going to just sit there while that returns. The question is, what's it going to do? Will I need nose surgery? What's a nose surgeon called?
Rhinoplasty.
Rhinoplasty?
Come back to the same
Not sure momentum's the key concept here.
Because it's not gathering more force as it's coming back at you. So
Momentum
you
and force. No, I believe we're mixing up concepts which don't help us. Francesca.
I don't know, but I think maybe it would come back a little bit stronger maybe the first time.
Stronger. So we have momentum, forces, stronger.
With
Energy.
It's considered.
Energy is what? Conserved, yeah, because obviously that's one of our key ideas. Energy is conserved. Philip, do you want to add something to the conversation?
I figure I might as well try. So, if it is energy that's like being conserved, is some energy being lost due to like the way the pendulum is moving?
So how would a pendulum lose energy? No.
Actually, that doesn't make
Hang on,
any
I'm going to switch to Nadia for this one. Nadia, how would a pendulum, how would this lose energy?
Air resistant?
Air resistance, very nice. It actually heats the air up. Impact with the molecules obviously slows it down, very nice. So, do you think that every cycle it's going to lose a little bit of energy?
Yes.
Cool. Okay, what kind of energy are we starting off with here?
potential.
Gravitational potential energy. And say, what's it going to convert that to?
Kinetic motion.
Where's the maximum kinetic energy, Tyra? Where's the maximum kinetic energy during the swing? Do you want to watch it and have a look? Where do you think it's going the fastest? Yep. Where's it going fastest? Vague. There is one position, Julia, where it's going the fastest. You are feeling sleepy. You are looking, it's like watching people at Wimbledon. Or cuckoo clock designers. It's like in the middle. Oddly enough, is this the lowest point?
Yeah.
So if you were comparing energies, up here it has potential. Down here, does it have any potential left?
No.
No, that's as low as it can go.
So, when the potential is as low as it can be, the kinetic energy is the highest?
So this very simple machine converts potential to kinetic to potential and back again. But every time you convert energy from one form to another, guess what happens? Some is lost, which is good news. Or I'm going to need rhinoplasty. Now, one of the things you must not move, so you mustn't move, and you have to, and it's much more exciting when it's a piece of steel.
I thought you said it was lead.
Yeah, that was lead. Yeah. So you just, and the thing you can't do, of course, is push it, because if you give it some initial kinetic energy, then it's got more energy here, and it's going to come back higher, and that will smush your nose. I have actually seen someone do that with a bowling ball and a steel wire, a very long steel wire, in a big auditorium, and astonishingly, he pushed it slightly and leaned in slightly. And I said to the person next to me, "Did you push that?" Broken nose, and the guy leaned back to me and said, "Yep." Really cool. And it's quite disturbing because the change in motion is called simple harmonic, and it's not linear, which means that most of the slowing down occurs at the end. So it's going really fast even when it's here, and it gives you the illusion it's going to smush your face. And of course it doesn't. If you use something smooth and heavier, the lights won't take it. It actually loses less energy each cycle, so it comes clear. He did flinch a bit, right?
I did.
He did, because it.
Hard not to.
Yeah, it's very hard not to. Try it again and try and remain composed. Better.
Okay.
You look catatonic now. That's good. Don't leave in. Oh, Miss Cool. Whack. Of course, this is like a fast.
And then let's look at some equations. The GPE, the kinetic energy, the work, omega, force times distance, and the power, omega over t. And with total conservation of energy, the object's potential energy would be converted totally into kinetic energy. And the bowling ball, the softball, would continue to swing with constant amplitude. But this does not happen. The hook, the pivot, isn't frictionless. There is friction between the ball and the air, and indeed between the string, the twine, and the air. And we can calculate the ball's potential energy and its kinetic energy, and the difference between the two equals the energy lost, predominantly as heat energy. I suppose if it's travelling really fast, there might be some sound energy, but I don't think we'd hear any in this example. And just a note about pendulum clocks. And the pendulum clock keeps accurate time and a constant amplitude. It does go to point B, but that's because there's extra energy available to compensate for friction. And the pendulum clocks do stop because the energy provided by the tightly coiled spring will lose its potential energy and it needs rewinding or will stop when wound down. With many thanks to the students in Mr. Godwin's physics class and Washington International School Team Science.